Hi, so welcome to today's video. Today's video is on irradiance, and it's the next topic in higher. So, what is irradiance? Irradiance is more or less just a fancy word for brightness. Okay, just how bright something is. The physicsy definition of irradiance, though, isn't just brightness. It is defined by the power incident on a surface per unit area. So the power falling on a surface per unit area, and is defined by this formula. So if you are struggling with a definition, what I always suggest you do is look at the formula and then just say what you see. So irradiance in this case is I, and it's measured in watts per meters squared. So irradiance is equal to the power per area, okay? So it's just power incident per unit area. Or just, you would even get the mark just for saying power per unit area. Okay, so that is the definition of irradiance, but just remember irradiance is just brightness. Okay, so you have irradiance measured in watts per meter squared is equal to power in watts divided by area in meters squared. Has to be meters squared, watch out for that. So just a wee worked example, a laser of power 0.1 milliwatts illuminates an area of 1 millimeter squared. Calculate the irradiance of the area of the laser. So power, simply just 0.1 milliwatts or 0.1 times 10 to the negative 3 watts. 1 millimeter squared. Now, I put this in for a reason, okay? Because it's not just as easy as putting a times 10 to the negative 3 in here because it's squared. Okay, you have 1 millimeter squared is actually equal to 1 times 10 to the negative 6 meters squared. Okay, I have a little note down the bottom here about to pop up to explain this, so I'll explain that in a second. And irradiance is what we're trying to work out, so just simply plug in what you know and you get an irradiance of 100 watts per meter squared. Now, to change millimeter squared into meter squared, divide by a million. Okay, you divide by a million because a square in a square meter there is 1,000 millimeters times 1,000 millimeters, because a square meter is 100 centimeters by 100 centimeters, or 1,000 millimeters by 1,000 millimeters. So 1,000 times 1,000 is a million. Okay, so that's why you divide by a million, because there are a million square millimeters in a square meter. Okay, so please just watch out for that. It's a little bit trickier. And they do sometimes use millimeter square to kind of catch you out a wee bit. Not often, but just watch out for that. So nice and easy, nothing too tricky about this formula, to be honest. Okay, at this point, we would usually do a wee experiment. Okay, and this is just to see the relationship between irradiance and distance. So we would have some sort of point light source. Now, when I say a point source of light, what I mean by that is a light source that illuminates all around the source. So, for example, a light bulb. A light bulb illuminates the whole area around it. A star illuminates the whole area around it. Okay, so that is a point source of light. So get a point source of light, like a bulb, and we would have a light detector, and we would measure the irradiance of the bulb at certain set distances, and then we would plot a graph. Now, the first graph we would get would look something like this. Okay, ignore the this because I've done it in centimeters, just the shape I just want you to look at. So we can see what we would expect. Okay, the further away you are from the light source, the lower the irradiance. Easy peasy lemon squeezy, okay? The further you are away from a light, the duller it'll seem. The closer you are to the light source, the brighter it'll seem. Nice and easy. But in physics, we don't really like to deal with slopey graphs because they're not as easy to put into a formula. We like straight line graphs. So it turns out if you take the distance, square it and then divide it by 1, you get a nice straight line graph like this that goes through the origin. So you have the irradiance up this side, and you have 1 divided by distance squared down here. Now, this is called an inverse square law, because if something is, oh, the word's just, sorry, I had to pause there because that word just totally left my mind. Yeah, so we call this the inverse square law, okay, and that's because if we say that something is proportional to something, if we have, for example, like y is equal to kx, okay, k being a constant, that would mean that y and x were proportional to each other. We say that something is inversely proportional to each other if like y was equal to 1 over x, okay? It's the inversely proportional. We say that this is an inverse square law because we square the thing that's on the bottom, okay? So you will see it referenced as the inverse square law quite a lot in higher, okay, this irradiance equation that we're just about to cover. Okay, so we can see that we have a nice constant gradient, okay, and because we have a constant gradient, we can make a nice formula out of this. And our formula is irradiance is equal to a constant divided by distance squared. Okay, our constant actually being the gradient of that graph. Okay, this means that distance squared multiplied by irradiance is equal to a constant. Okay, where I is just irradiance distance, or d is just the distance from the light source in meters, and k is a constant. Now, because it's just constant, it doesn't have units. A constant, the constant for irradiance is different for each light source. So if you're dealing with a bulb X, okay, if you work out that the constant for bulb X is 5, it will always be 5, okay? But then if you look at bulb Y, you might find that bulb Y has a constant of 2, and it will always be 2 for that bulb, but the constants do change depending on what light source you are looking at. So, worked example, a light source has an irradiance of 3 watts per meter squared at a distance of 2 meters. What would its irradiance be at a distance of 5 meters? So, first off, we're trying to work out its irradiance at 5 meters, but to do that, we need to work out its constant. So we can do that using this information. So we have the irradiance is 3, the distance is 2. Okay, so we can just pop it into this formula to find out that the constant for this light source is 12. Okay, therefore, we know it's constant now, and we know that its new distance is 5 meters, so we can work out its irradiance, and we find that its irradiance is 0.48 watts per meter squared. Please don't forget to square your distance. I see that quite a lot, just people making silly wee mistakes. Also, use your common sense here. It's increasing its distance, so it's getting duller. Yeah, it's going to be dimmer. So you're expecting your irradiance to be smaller than it originally was. If you have a higher irradiance, you know you've done something wrong. This is just a wee visual representation of what's happening here. So each of these little lines is just sort of representing brightness. So you can see that at distance 1, okay, that you have all of the irradiance is focused on one area. Okay, but then if you go to distance 2, you can see that these rays of light are now spread out. So you have less irradiance, or the same irradiance, but over a larger area. Okay, and then at area 3, again, you have the same amount of light rays, but they are now spread over an even greater area. So you'll find that it appears less bright. Now, importantly, I spoke about this earlier, talking about point light sources. It's important to note that this formula only works for point sources of light. So e.g. like light bulbs and stars and things like that, things that irradiate all around them. Lasers do not follow this law. It does not work for lasers. Lasers are fine for the first formula, radiance is equal to power over area, but lasers do not follow the inverse square law. And that's because we say that lasers are irradiant, which means that a perfect laser actually remains the same brightness at any distance. Okay, obviously that's not quite true in the real world, but in theory, a perfect laser remains the same brightness at all distances. Okay, so it doesn't actually follow this formula. Quite a common wee exam question. They might ask, why would this experiment not produce the same results with the laser? And you would just be like, it is not a light, so it is not a point source. Or another one would be, what assumptions are we making about this experiment? They might be doing the same experiment that I showed you earlier, and it would be like that the light source is a point source of light. Okay, so just a few wee examples there. And that is irradiance. It's quite a wee short topic. Okay, yeah, that's us for today.